to Friday Happy Math Hour. Today we are going to be doing some review, some of the material that you should see on your third exam. My name is Melinda Camarillo, and I'll be going over some examples and some review questions that could help you out. Okay, so some of the things that you should have seen recently were working with sequences, right? So for example, writing the nth term of a sequence. So we have a few sequences here, and we're asked to find an expression for the nth term of each sequence. So let's look at the first one. We have A, which is 1, 3, 5, 7. It continues on. One strategy is to look for the differences between these numbers in our sequence. So between 1 and 3, we have a difference of 2. Between 3 and 5, we have another difference of 2. Between 5 and 7, the difference is also 2. So if we need to write an expression, something that gives us the terms of the sequence, let's start with something with a 2, such as 2 times n. So remember that n represents the position of the term in the sequence. So n being 1 would be for the first term. If you plug in a 2 for n, that's for the second term. And the output should give you the value of the term, right? So let's check this one. So 2n, if we plug in a 1, then it should give us that first term, which is a 1. But when I plug in a 1 for n, 1 times 2 is 2, so that's not the first term of the sequence, so that's not going to work. But we can work with this 2n. So what if we try 2n minus 1? Because we noticed over here that the value is 2, but I wanted a 1. So let's see if minusing 1 helps us out. So let's check this one. So what if I plug in a 1, which means I want to generate the first term, which is a 1. So plugging in a 1 for n, 2 times 1 is 2 minus 1. 2 minus 1 is 1, and it does check. That is the first term. So a sub 1 is 1. Now, what if I plug in another number just to check? What if I plug in a 4 for n? So that's the fourth term. So the fourth term should be a 7. So plugging in a 4 here should give me the 7. So let's see. 2 times 4 minus 1 is 8 minus 1. 8 minus 1 is 7. So it does work. So that would be the expression here that gives us this sequence, right? The terms of the sequence, 2n minus 1. So let's try the next one, part B. 2, negative 5, 10, negative 17. Now, remember that when we have alternating signs, we have to account for that, right? So n begins with 1. Here are our options. We're going to have to use negative 1 to the n if our first term is negative, or negative 1 to the n plus 1 if the first term is positive. So again, we have alternating signs here. We start with positive, negative, then positive, negative, and our first term is positive. So we're going to have to use this negative 1 to the n plus 1 as part of our expression, okay? So now let's work with the rest of it to see what other formula we're going to have. So if we take the differences here, between 5 and 2, it's 3. Between 10 and 5, it's 5. Between 17 and 10, it's 7. So we're ignoring the negative right now because we're going to deal with the signs with this part of the equation over here. Taking the differences here, I don't see a constant difference. So I'm going to take the differences of these differences. So between 5 and 3, I get a 2. Between 7 and 5, I get another 2. So now I have a constant difference of 2. But because it took me 2 sets of differences to get there, that means power of 2. So I'm going to look at quadratic expressions here, okay? Quadratic because it took 2 stages of getting differences in order to start with the same number, same difference, right? So let's just start with n squared, right? So let's check it. So if I plug in a 1 squared, I get a 1. I'm supposed to get a 2 because that's the first term. I didn't. So that didn't work, but let's play with it. So I'm going to try n squared plus 1. Why? Because when I plugged in a 1, I got a 1, but I wanted a 2. So let's see if adding 1 is going to help me get that value that I wanted. So now I plug it in here, my first term. I should get a 2, so I plug in a 1 as my first term. So 1 squared plus 1 squared is 1 plus 1 is 2. So it worked for that one, but I'm going to try it again. Let's plug in a 4. So I should get the 17. Now, the negative is going to come from using this part of the expression. So right now I'm just going to see if I get the 17. So I plug in a 4. 4 squared plus 1. 4 squared is 16. 16 plus 1 is 17. So a sub 4 is 17. So that works. So I'm going to use n squared plus 1 in my expression along with -1 of the n plus 1. That's going to give me the alternating signs starting with the first term positive. So that should be the expression that I use for this one. So again, if you need to write an expression for the terms of a sequence for the nth term, start by looking at the differences amongst the term, and how many differences it takes you determines the type of equation. You can play with that. Okay, here we have a recursive sequence. We want to write the first 5 terms of the sequence as defined recursively. That means that the previous terms help you generate the next terms. So this one starts with a sub 0. If a sub 0 is 1, a sub 1 is 2, then terms following that, a sub k, you're going to get a sub k minus 2. So you go 2 terms before that one, plus 1/2 a sub k minus 1, which is the term right before that one. So that's how this one is defined. So we want the first 5 terms. Well, we have the first term, a sub 0 is 1. We have the next term, a sub 1 is 2. So here is our equation. We're going to use the equation to get the next term. So now I want a sub 2. So I plug in a 2 for k right here, right? So that's going to be a sub 2 minus 2 plus 1/2 a sub 2 minus 1. Reducing here, 2 minus 2 is 0. So I want term a sub 0 plus a sub 2 minus 1. 2 minus 1 is 1. So I want a sub 0 plus 1/2 times a sub 1. So I'm going to plug in those values. A sub 0 is 1. A sub 1 is 2. So I plug those values in. So you see, you need the previous terms in order to get this term here. So a sub 0 is 1. 1/2. A sub 1 is 2. 1 plus 1/2 times 2 is 1. 1 plus 1 is 2. So the next term here is 2. We want the first 5 terms, so continuing on. A sub 3, plug in a 3. We want a sub 3 minus 2 plus 1/2 a sub 3 minus 1. Simplifying, 3 minus 2 is 1, so I want a sub 1. 3 minus 1 is 2 plus 1/2 a sub 2. So a sub 1, I plug in those values. What did I get? A sub 1 was 2. And a sub 2 is the one I got previously. So we're plugging in the term two terms before, which was the 2, plus 1/2 times the term right before 1/2 times 2. Simplifying here, 1/2 times 2 is 1. 2 plus 1 is 3, and that's what I get for that one. A sub 4, so when I plug in a 4, simplifying, 4 minus 2 is 2. 4 minus 1 is 3. So I want a sub 2 plus 1/2 times a sub 3. So I want 2 terms before here. So 2 terms before, I want to plug in the 2. And 1 term before is the 3. So plugging that in, 2 plus 1/2 times 3. 2 plus 3 over 2. And simplifying, I get 7 over 2. So here are my 5 terms. Okay, oops. I have 1, 2, 2, 3, and 7 over 2. Those are the first 5 terms of the sequence. Okay, so the nth term of an arithmetic sequence, we have a formula here. If you recall, an arithmetic sequence is a sequence that has a common difference amongst the terms. So we can use this formula here to generate any of the terms. A sub n is going to be a sub 1, which is the first term, plus n minus 1 times that common difference, okay? So let's do an example here. We have find a formula for the nth term of the arithmetic sequence whose common difference is 3 and whose first term is 2. So we have these values. The first term is 2, so a sub 1 is 2. The common difference is 3. That means d is 3. So here's our formula. We're just going to plug these values into the formula. A sub 1 is 2. D is 3. We plug that in. When I distribute the 3, I get 3n minus 3. Simplifying, combining like terms, 3n, negative 3 plus 2 is minus 1. And that's going to be our formula for the nth term. Okay. Next, write the term of the arithmetic sequence whose fourth term is 20 and 13th term is 65, and then write the first 11 terms of the sequence. Okay, so we're going to need the first term, a sub 1, and the difference. Like in the previous example, we had a sub 1, we had the difference. We were able to get the formula from that. Okay, but we know that A4 is 20, A13 is 65, so somehow we need to use these to help us out. So as you recall from previously when we did the lesson, one way to do this one is to just kind of list the terms. So I have the 13 slots here for the first 13 terms of this sequence. I know the fourth term is 20, so I write that down. I know the 13th term is 65, so I have that down. So I need to take the difference not only between these values, but between their position in the sequence, okay? So there's 9 terms between them. So what I'm going to do is I'm going to not only subtract the terms, take 65 minus 20, which is 45, and subtract their position, right? The 13 minus 4 is 9. And when I divide the 45 and the 9, that's how I get their common difference, the D. So again, if you recall from before when we've done this lesson, the observation here, shortcut way to kind of do it is list these, right? We have A13 is 65. A sub 4 is 20, and we're subtracting all of these, right? 13 minus 4 is 9. 65 minus 20 is 45. Those are the values we divide to give us the common difference. Now, I'm going to show you how to get everything with the formula, but now that you know the common difference is 5, you can just keep adding 5 each time to get your next terms, or if we go backwards, you can keep subtracting 5. So if I have 20, minus 5 is 15, minus 5 is 10, minus 5 is 5. So I can go ahead and find a sub 1 just by subtracting the difference if I needed to. Okay, and then I can get the rest of these terms if I needed to just by adding 5 each time once you have that common difference. Okay, so keep in mind that's one way to do it. I'm going to continue on though showing you how to do this with the formula. So here's our formula from before for an arithmetic sequence. Plugging in what I know. Well, I know a sub 4 is 20, so I'm going to plug in those values. N is going to be 4. I'm going to use my a sub 4, my 20. I know the D is 5. I plug that in. The a sub 4 value is 20, so I plug in a 20 for a sub 4. So I'm going to take this to just solve for a sub 1, okay? If I simplify here, 4 minus 1 is 3. 3 times 5 is going to be 15. Solve, subtract 15 from both sides to get a 1, and I do get a 1 is 5, which I had mentioned before we can get from just subtracting that common difference, okay? But there we go, we have the 5. Now, again, I know the common difference is 5, so I can just add 5 each time and get the next terms, or I can also continue by using the formula now. So I can go ahead and get a general formula here. A sub n is going to be a sub 1, which is 5 now. D is 5, and I plug these in to get a general formula here. So distribute 5 times n minus 1. The 5 minus 5 cancels. So my formula then for this sequence is just a sub n equals 5n. So if I wanted any other term, for example, if I wanted the next term, a sub 2, I plug in a 2 for n. 5 times 2 is 10, so my next term is 10. And I can continue on. I can plug in the 3, the 4, and all the rest of the n's to get the terms of the sequence, right? Or, like I said, just keep adding 5 each time. So plus 5 is 15, plus 5 is 20, plus 5 is 25, and so on to generate the next terms. Now, it only wants the first 11 terms, so I'm done once I hit the 55. And those would be the first the first 11 terms of this sequence. So again, showing you how to do it using the formula and the steps, or most importantly, once you find that common difference, you can use that to find the terms if you need it. The formula helps because it can help you get any term you need, even larger term values, right? It's easy to just add 5 for the first few times, but if I wanted like the 150th term, that might take a while, so that's when the formula comes in handy. Okay, so like in this one, we're going to find the 150th partial sum of the arithmetic sequence. So there is a formula for this we have, okay? In the formula, we're going to plug in the first term and the 150th term because I want the sum for the 150th terms. Here is your formula. If you recall, S for sum, S sub n equals n over 2 times a sub 1 plus a sub n. So you need the first term, and like I mentioned before, the 150th term. N is the 150 because I want the 150th partial sum. I know the first term is 5, so I'm going to use my formula here to help me get the next term, okay? The 150th term. So right here, in order to finish with the formula, I also need D, okay? So I have a sub 1, I can plug that in. D, I'm going to need as well to plug in to find the general formula for this one, right? So how do I find D? Well, I have these terms, I just subtract common difference. So 16 minus 5 is 11. So that should be my D, a common difference. So now plugging all that in, I have the first term, I have the difference. Now I'm just going to solve here so that I have the formula for any term, for any n term of the sequence. So again, distributing here, 11 times n, 11 times negative 1, 11n minus 11. Simplifying, 5 minus 11 is negative 6. So now my formula to generate any term of the sequence is going to be 11n minus 6. So how am I going to use this formula? Well, I need the 150th term. So I'm going to plug in 150 for n to get the 150th term. So a sub 150 equals 11 times, again, n is 150 minus 6. 11 times 150 minus 6 should give me 1644. So again, I'm up here, I need the sum. So for the sum, I need the first term and the 150th term. The formula helped me get the 150th term. Now that I have it, I'm able to plug it all into the formula. So again, I have the first term, I got my 150th term. I'm going to use the formula to plug that all in. N is 150 over 2. A sub 1 is 5 plus a sub n, the 1644. 150 over 2 is 75. 5 plus 1644 is 1649. Multiply there, and we get that the sum is 123,675. So you have the formula here again to use partial sum for an arithmetic sequence. You just have to take the information that you have and use some of the other information to get whatever else you needed, like in this case, the 150th term. Okay, so now we're going to find the 15th term for a geometric sequence. The first term is 20. The common ratio is 1.05. So again, we have the first term 20. We have the R 1.05. We need the 15th term. So how are we going to do it? Okay, let's list again what we have here. I want the 15th term. Well, this is the formula. So we were previously doing arithmetic sequences. I gave you that formula and doing examples, but we have a formula for generating terms of a geometric sequence. It's a sub n equals a sub 1, the first term, times r, which is our ratio, to the power of that n minus 1. So I'm going to plug in what I have, or what I need here. I need a sub 15. So n is 15. I do have a sub 1, which is 20. I have my r, which is 1.05. N is 15. 15 minus 1, that's what gets plugged in. Simplifying here, 15 minus 1 is 14. So taking this into your calculator, 20 times 1.05 to the 14th power, we get 39.59863199, but we can round. So pay attention to how they want you to round this one. It might round to 2 decimal places, 39.598. The 8 makes it 0.60 if I'm rounding to 2 decimal places. So that would be my 15th term. So again, pay attention as you're working with sequences. There's arithmetic sequences, and we have formulas to use with those type of sequences. There's geometric sequences, and we have formulas to use, particularly this one right here for a geometric sequence. Okay, so keep that in mind. Geometric also includes an R, or ratio, whereas an arithmetic includes a D, which is a common difference. Okay, so find a formula for the nth term of a geometric sequence. And then what is the 12th term of the sequence? So here's a geometric sequence, okay? We have A1, which is 5. What we need to do is find the ratio, R, and then use the formula. So how do we find the ratio? Well, geometric sequences, you just divide. Well, geometric sequence, you're always multiplying by a number, right, to get the next number. So if we're going to find that number, work backwards, we can divide. Take a term and divide it by its previous term here, right? So we can do 15 divided by 5 or 45 divided by 15 as well. And those should be the same. That'll be our ratio for the geometric sequence. So here, 45 divided by 15 is 3. If we check again, 15 divided by 5 is 3. So that is our ratio. Okay, we're always going to continue on getting more numbers by multiplying by 3. But again, to check and find that, we divide. Okay, so I have again, A1 is 5. Now I found that my ratio is 3. I want to find the 12th term. Well, again, I know it's geometric, so this is my formula for any term of a geometric sequence. A sub n is 12, so I plug in 12. I have A1 is 5, my ratio is 3, and I plug in 12 for n, 12 minus 1. 12 minus 1 is 11. Order of operations, you're going to do 3 to the 11th power first and then times 5, or you can just plug all this appropriately into your calculator, and we should get 885,735. So that's a big number. Geometric sequences grow pretty rapidly, increase pretty rapidly, because you're multiplying by a number each time. Okay, finding the term of a geometric sequence, another example. So the 4th term of a geometric sequence is 125. The 10th term is 125 over 64. So we want to find the 14th term and assume that the terms are all positive. Okay, so we want to find r and a sub 1. But what do I have? I have that the 4th term is 125, so a sub 4 is 125. The 10th term, so a sub 10 is 125 over 64. We want a sub 14. So I'm going to list this out like we did before, right? All the slots represent the terms of the sequence. I know that the 4th term is 125, and I know that the 10th term is 125 over 14. What I'm asking for is that last term. So it's similar to an example we did previously, but the previous example was geometric, and the previous example was arithmetic. This one is geometric. So we had our techniques for doing this one before when it was arithmetic. So let's look at how we do this one when it's geometric. We take the formula for the geometric sequence, and we're going to plug in what we have. So for a sub 10, we plug in the values here. For a sub 4, we plug in the values that we have here. And if you recall from last time, we subtracted what do we have? This time we're going to divide. So we divide what we get when we plug in the 10 into the formula and by what we get when we plug in the 4 into the formula. Okay? A sub 1's cancel. R to the 10 minus 1, 10 minus 1 is 9. Divided by r to the 4 minus 1, 4 minus 1 is 3. So 9, r to the 9th divided by I to the 3rd, r to the 3rd. If you recall, to divide powers, we subtract them. So we're going to get r to the 9 minus 3, which is r to the 6. And when we divide right here, we have 125 over 4 divided by 125. So we get r to the 6, the 125's cancel, 1 over 64. So I'm trying to solve for r. This is the technique we use. R is to the 6th power. So to get r, we either take the 6th root of r or take it to the 1/6 power. So I'm going to go ahead and raise both sides to the 1/6 power so that the 6 cancels with the 1/6. So r equals 1 over 64 to the power of 1/6. You can use your calculators and then simplify, and we end up with 1 over 2. Okay, so again, power of 1/6 is the same as the 6th root. The 6th root of 64 would be 2, so it does reduce to 1 over 2. So I got my r value that way by dividing over here. So again, going back to our formula, let me plug in what I can. I now know r, 1/2. I have a sub 4 value, so I'm going to plug that in. So n is 4. A sub 4 was 125, so I'm using that number. So 125 equals a sub 1 times 1/2 to the 3rd. 1/2 to the 3rd is 1/8. Now I'm trying to get the value for a sub 1, so I need to get rid of 1 over 8. So we multiply by 8 on both sides, multiply by the reciprocal here. So a sub 1 is 125 times 8, which is 1,000. Okay, so I have that. So just like previously, remember it was arithmetic. Once you have that common difference, you can keep adding each time. Well, now that we're geometric, we can keep multiplying by that r each time. So we can do that to find some of the terms if we needed to. So now I know that my first term is 1,000. Remember, my r is 1/2. So if I just keep multiplying by 1/2 each time, I'll be able to generate my next term. So half of 1,000 would be 500. Half of that would be 250. Half of that is 125. And I can keep going to get my next terms. Keep that in mind, right? Once you know your r and any of your terms. However, I'm going to continue on showing you with the formula. So a sub 1 was 1,000. R is 1/2. So I'm going to plug those in and just get a general formula so that I can get any term of the sequence that I need, okay? So 1,000 times 1/2 to the n minus 1 is going to be my general formula. So if I want my 14th term, I'm going to plug in a 14 for n. So I'm going to take 1,000 times 1/2 to the 13th power. Again, you can use your calculators, and we should get 125 over 1024. Again, you could also, from here, times 1/2, times 1/2, times 1/2, and times 1/2 to get to the value you need. So either of those work, okay? But again, using the formula might be more efficient with some of these values. So it should be 125 over 1024 for the 14th term. Okay, another example, find the sum. So this was something that you were also working on before, and you do have certain formulas as well. Okay, so just a lot of this is about finding the appropriate formula that you need for what you're working on. Okay, so here we have the formula for the sum right here. S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. So we need a sub 1, we need n, and we need r, so we can plug those into our formula here and get the sum. Okay, so how are we going to find a sub 1? We have this sum right here. It's going from 1 to 12. And here's the formula that we're going to use to generate each of the terms. So when you want the first term, that's plugging in a 1 for I, okay? So you're just going to take 1 to 1. It's just that one term, that's a sub 1. So if you plug in a 1 for I, that's going to be your first term. So 1 minus 1 is 0. So that's going to give me 0.3 to the 0 power, which is 1. And then 1 times 4, which is going to be 4. So I use that to get my a sub 1. Now, what is n? N is, well, I skipped, but we'll do r. We'll do n. N is 12. N is the number up here. So that's how many times we're doing this. If we want the sum from 1 to 12, that's 12 terms that we want to sum up, right? So that's our n, that's the 12. And then the ratio is the number that's raised to that power. The ratio is the number that you keep multiplying each time. So it's that number you're going to see raised to that power. So it's that number right here, the 0.3. So now that we have a sub 1, we have r, we have n, we can plug them into our formula, okay, into our equation. S sub 12, so the sum for the first 12 terms is going to equal a sub 1, which is 4, times 1 minus that r, 0.3 to the power of 12, time all over 1 minus 0.3 r. Simplify that using your calculator, and we round, it should be 5.714 for that sum for those first 12 terms for that one. Okay. Okay, some more review. From section 9.4, you're working on mathematical induction. So let's review some of these. The principle of mathematical induction. So let P sub n be a statement involving the positive integer n. 1. If P1 is true, and 2, for every positive integer k, the truth of P sub k implies the truth of k sub 1, then the statement P sub n must be true for all positive integers n. So this is the principle that we're using for mathematical induction. So basically, what does that mean? That means that when we're going to prove something with mathematical induction, 1, we have to show that it's true. Really, we can show that it's true for any n, any value, but usually we pick 1. So we show that it's true for some value, n sub 1, okay? So if it's true, then we assume it's true, that first statement, S sub k would be true. And then you have to show that it's true for k plus 1. So we're adding one more term to it. Okay, so we add k plus 1 on both sides, and then we use the previous assumption, S sub k, to show that the other one is true. So let's apply that to this example here, use mathematical induction. So this is S sub n. adding up all these numbers. This is the formula to generate each term. So if we're going to generate more terms, we can use that one based on the position of n. We're saying that all of this, the sum of all of this equals to n squared, okay, for all integers n greater than or equal to 1. Okay, so again, remember, we're going to have to prove that this is true for any integer. We're going to use n equals 1. If it's true, then we assume it's valid for some s sub k. We replace n for k because we've proven for another variable, k. And then we're going to show that it's true for one more term added on, the s sub k plus 1, and show that both sides equal each other. Okay, so here is my original statement here. Show that it's true for n equals 1. So we show the left side and the right side. So on the left side, this is the formula for generating any term. So if we plug in a 1, that should give us the first term. We're going to show that it's equal to plugging in a 1 on the right side as well. So on the left side, again, we have 2n minus 1. On the right side, we have the n squared. We're going to plug in a 1, and they have to match. So if I plug in a 1, 2 times 1 is 2 minus 1. 2 minus 1 is 1. Does that match if I plug in a 1 on the right side? If I plug in a 1, I get 1 squared. 1 squared is 1. So it does match. So it does work. Okay. Now, again, we can prove this. We can use any other integers, which I kind of like to show sometime. If we were going to show for n equals 2, that means the sum of the first two numbers. So the sum, if n equals 2, 1 plus this term is 4. And if I plug in a 2 over here, 2 squared is 4, so it does work. And we can continue on. So however many terms we want to add up, that's the n that we're plugging in. And it has to equal just plugging that n on the right side to the formula as well. But again, it's just more common to use the n equals 1. Okay, so we showed the first part. It is true for n equals 1. So next, we have to assume valid for s sub k. So we have the original s sub n, but we're going to replace it with a k because we haven't proven the s sub n statement first. We did prove it worked for one value, which was 1. So we're just going to assume that it works for some other value k. Okay, so here's that statement. Okay. Now we have to show this true for k plus 1, so we're adding one more term. So we're going to plug in a k plus 1 on both sides. Okay, so right here, this is the equation for any term. So what if I want it for the k plus 1 term? So I would add k plus 1. So now that formula becomes 2k plus 1 minus 1. Well, then I have to plug in k plus 1 on the other side. So instead of k squared, it's k plus 1 squared. So that's proving the next term, right? Adding the k plus 1. So you're going to use the original statement. You use your s sub k somehow in there because you always have the s sub k. We added that extra k plus 1, but we always have that s sub k. So notice this whole part is s sub k, and that equals k squared. So we're going to replace that. This whole part underlined in red is now k squared, right, from up here. Plus, we added this part, and if we distribute here, it's 2k plus 2 minus 1. We're going to simplify that right now. K squared plus 2 minus 1 is 1. So putting all this together, k squared plus 2k plus 1. If we factor this out, we're going to get it's k plus 1, k plus 1, okay? Or k plus 1 squared. So this was all just working on the left side. So on the left side, again, you're going to use your s sub k, which was up here, to simplify that part. Add it to the k plus 1 term that we put in, and then you simplify that, we get k plus 1 squared. Now that should always match up with what's on the right. Sometimes you need to simplify something on the right as well to get them to match. But we can see right here by factoring k plus 1 squared, this is our left side. It matches what we have on the right side. So that shows that this is true. And so that is how we use mathematical induction to prove a statement like this. The left and the right side end up being the same. Okay. All right, now let's do another example. We're going to prove that this formula is true using mathematical induction. Again, prove that it's true for some value, n equals 1. Then we assume it's true for some value k, and then show that it's true for s sub k plus 1. Okay, assume true for some n equals 1. So that's the first term. So this is the formula for any term. So for the first term, n is 1. I have to show that it equals all of this on the right, also plugging in a 1. So left side, 2n, right side, n plus 1, plug in a 1. 2n, plug in a 1 for n, I get a 2. On the right side, plug in a 1, 1 plus 1 times 1 is 2 times 1, which is 2, so it does work, okay? Now, again, it's supposed to be true for any n. So if I have a 2, that means it's the sum of the first 2 numbers. So if n was 2, I'm using 2 plus 4. That's the first 2 numbers. So 2 plus 4 is 6. And if I plug in a 2 over here, 2 plus 1 is 3 plus 2 is 6. It works. Okay, so it works not just for 1, it works for several values, but I just needed to show it was true for n equals 1, and it works. So now assume true. This is our statement S sub n, but we're going to assume true for some k. So again, I haven't proven that it's true for n, but I did prove it does work for some values, so we're going to call that a k. So this does work for some value, k, so we have it with k. Okay. Now we're going to show it's true for S sub k plus 1, so we're going to plug in the k plus 1. So we have all of this. We're going to add one more term, so that would be the S k plus 1 term. So I plug in k plus 1 for k. On the right side as well, if it was true for k plus 1, I'm plugging in a k plus 1 for k. So it's k plus 1 out here times parentheses k plus 1 plus 1, k plus 1 plus 1. So let's simplify a little bit, okay? Right here on the right side, I'm simplifying k plus 1. K plus 1 plus 1 is k plus 2. Again, you're going to always use all of this. Replace that with your S sub k value right here. So all of this, 2 all the way to 2k, is equal to k plus 1. So I'm going to replace that with the k plus 1. All of this in red equals the k plus 1 from up here. Now I'm going to add the 2k plus 1. Now I need to simplify this so that it matches on the right side. Now on the right side, I simplified a little bit. That's what I got. I need this to look like that. Well, if you notice, I have a k plus 1 term here, so I can factor that out. So this is going to factor, pull out k plus 1, and what's left? K plus 2. K plus 1 times k plus 2. And what do you know? They match. They're equal. So by induction, these match, so it is true. Okay, proof is done. Okay, so some of the other sections you looked at were also binomial expansions, working with binomial expansions here. So we're going to start here. Write the expansion of this expression. So if you remember, this is the formula that we have. You can also use Pascal's triangle to get all these coefficients that we have as well. So whatever works for you, right? If this is x plus 2 to the 4th power, we use this 4th row right here, and the numbers highlighted in blue are the values, our coefficients in front, okay? Using the formula, though, I'm going to plug in n represents the power, and then we start with 0 all the way up until we get n matches with n. So for ours, the way I get my coefficients is going to be n, which is 4. So I start with 4, 0, 4, 1, 4, 2, 4, 3 to 4, 4. And if you recall then, okay, here if you see from the formula 2a, or the first term, starts with being raised to the n power. B, or the next term, starts being raised to the 0 power. And then with the first term, n, you decrease it, so then it's minus 1, minus another 1. With b, the second term, you increase it, so 0, 1, and so on and so forth. So that's what we do here. X starts to the 4th power, x to the 4, then 3, then 2, then 1, then 0. And then our next term is 2. We start with that term to the 0 power and increase 1, 2, 3, all the way to 4 till we get to n, okay? The numbers in front, if you recall, we do have a formula to get that, but we can also remember that they would match here from the triangle. So the values for these coefficients, 1, 4, 6, 4, and 1, those are the values there. And then we're going to simplify the rest. So here, 4, 0 is 1, x to the 4th, 2 to the 0 is 1. 4, 1 is 4, x to the 3rd, 2 to the 1st is 2. 4, 2 is 6, x squared is x squared, 2 squared is 4, so on and so forth. So we have 4x times 8, and here we have 1 times 16. Putting it all together, multiplying to get each of your terms, we have 1x to the 4th, 4 and 2 is 8, so 8x cubed. 6 and 4 is 24, so 24x squared. 4 and 8 is 32, 32x, and multiplying 1 and 1 and 16 is 16. So that would be the expansion for x plus 2 to the 4th power. Here's another one. Okay, from the coefficients, Pascal's triangle, that's what we have. Same thing as if we were to use the formula and do the coefficient. So we have that. But let's see how we generated the rest of them. So the first term here is 2x. You raise that to the fifth power. Then you take for the next term 2x to the 4, go down by 1, 2x to the third, 2x squared, 2x to the first, 2x to the 0. Our next term here is a negative y. So we have negative y, and we start with 0, but then we increase each time. Negative y to the 1, to the 2, to the 3, to the 4, and to the 5. Now we have to simplify all of this, okay? So 5 and 0 is 1. 2 to the 5th is 32. X to the 5th is x to the 5th. Negative y, or anything that's 0 power, is 1. So I'm simplifying all of that, right? 5, 1 is 5. 2 to the 4th is 16. X to the 4th. Negative y to the first power is negative y. So I continue on. 5 and 2 is 10. This simplifies 8x to the third, and negative y squared becomes positive y squared. Then I get 10, 4 squared, 4x squared. Negative to the third is still negative, so negative y squared. Here I have 5. 2x to the first is 2x. Negative y to the fourth is a positive. And then over here I have 1. 2x to the 0 is 1. And negative to the fifth power is a negative y to the fifth. So then I simplify each term. 1 and 1 times 32 is 32. I have a negative with 16 and 5, negative 80, x to the fourth y. I have 10 times 8, which is 80, x to the third y squared. Over here, 10 and 4, and negative is negative 40. Here, 5 and 2 is 10 y to the fourth, and my last one is 1 times negative y to the fifth. So that is the expansion for this one. Another example, I have y minus 3 to the third. So again, first I'm going to set up each of my terms. My first term is y. So you take that to the third power, and then we're going to go down by 1 for every consecutive term. And then next term is negative 3. I start with negative 3 to the 0 power, but I'm going to go up each time until I get to 3. So let's look at that. So next is y squared. I go down by 1. The next term goes up by 1. Then y and negative 3 squared. Then y to 0 and 3. Coefficients, we start with n. 3, 0, 3, 1, 3, 2, and 3, 3. You can use the formula we've done before or Pascal's triangle to get those values. So simplified here, 1, y to the third, anything to 0 is 1. We have 3y squared, negative 3 to the first is negative 3. We have 3y, negative 3 squared is 9. And then here we have 1, 1, and negative 27. So we have y to the third, simplifying each term, negative 3y squared plus 27y and minus 27. That would be the expansion for that one. Okay, what if we just want a specific term? I don't want the whole expansion. Okay, so this would be the whole expansion, but remember, each of these represents a term. This is the first term, this is the second, this is the third, this is the fourth, and so on. So when you want a specific term, like the fourth term, we only want this value right here. We don't need to do the whole expansion. Okay, so how does that relate? Well, the r value that I'm going to use, the coefficient, is 1 less than the term I want. So I want the fourth term. Notice the r value in the bottom is 1 less, 3. If you want the third term, r on the bottom is 1 less, 2. Okay, so we're going to use that. N is always the power of the binomial, so n is 7. Okay, so my fourth term, nr, my coefficient, is going to be with 7 and 3. Okay, again, 1 less than the term, the r on the bottom. Now, what is A? A is the 3x. B is the 2y. So I'm going to plug that in. Now, remember, and then I have 7, 3. Now, remember that the second term, like the 2y, the power is going to match the r. Okay, so that helps us. So I have the 3. So the 2y is going to be raised to the third power. And also remember that the powers of the 2 have to add up to n. Okay, in this case, 7. So if I know that the 2y has to be raised to the third power, and I know that the 2 powers have to add up to 7, well, 3x has to be raised to the fourth power. Okay, so this is my setup to find just that term. Okay, so when I do my calculations here, I get 35, 3x to the fourth. So 3 to the fourth is 81, x to the fourth, and then 2y to the third. 2 to the third is 8, and then times y to the third. Multiply all of the coefficients, 35 times 81 times 8, with x to the fourth and y to the third. So for this one term, I get 22,680 x to the fourth, y to the third, and that is just finding that one term of the expansion. So let's do this one more time. We want the eighth term. Again, this is how we get all the terms, but specifically I want the eighth one for this expansion. So this is 6x plus 2y to the power of 9. So 9 is my n, okay? Now remember that r is 1 less than the term. So if I want the eighth term, r is going to be 7 in this case, okay? So I want the eighth term, n is 9. R is 1 less than the term that I want, so 7, okay? So here is the expression. 6x is the A, 2y is the B. So remember, the second part of it, the 2y, is going to be raised to the same power of r. So 9, 7 is how I find the coefficient. R is 7, so the second term is the same power, raised to the 7th power. Now remember, these two have to add up to 9. So it has to be a 2. 7 plus 2 is 9. So simplifying here, I get 36. 6 squared is also 36 times x squared. 2y to the 7th, 2 to the 7th is 128. Y to the 7th, multiply everything all out. We get 165,888 times x squared, y to the 7th. Okay, so now we're moving on. If you remember at the end, you should have gone over counting techniques as well as probability. So now we're going to look at that. We're going to start with some counting techniques here with this example. License plate numbers. In a certain state, each automobile license plate number consists of 2 letters followed by a 4-digit number. To avoid confusion between O and 0 and between I and 1, the letters O and I are not used. So how many distinct license plate numbers are possible? Okay, so this is 2 examples. So in the first one, we're looking here, we have 2 letters followed by a 4-digit number. So we have 2 letters that we're going to pick from, and then we have 4 numbers that we can pick from, okay, digits, 0 through 10, okay? It says the letters O and I are not used, so out of the 26 letters of the alphabet, we can't use those 2. So we only have 24 letters to pick from. So we have 24 letters to pick from each time, so 24 times 24. If you recall by the counting principle, we're going to list out all the possibilities for each of these options, and then we multiply them. So how many ways can we pick the letters? 24 options. There's another letter, there's another 24 options, so we multiply. But then we also want 4 digits, okay? And how many digits are there? Well, 0 through 9, there's 10 digits, okay? So we have times 10, times 10, times 10, and times 10 for all our options. Multiply all of this out. 24 times 24 times 10 times 10 times 10 times 10. You should get 5,760,000 for this one, okay? So we're going to do a similar one, but kind of change it up a little bit. So how many different license plates are possible if each contains 3 letters followed by 3 digits? And then we're going to do how many of these license plates contain no repeated letters and no repeated digits. So let's look at that. Okay, so keep in mind there are 26 letters of the alphabet and 10 digits. So let's do the first one. How many different license plates are possible with that first arrangement? So you have 3 letters followed by 3 digits. So again, the first 3 choices are letters. The next 3 are digits, and that's it. So we know there's 26 letters of the alphabet. So for each option of those 3 letters, I have 26 choices. So I'm going to multiply them all out. We have 10 choices for the digits. So to find how many possibilities there are with this arrangement, we just multiply everything. 26 times 26 times 26 times 10 times 10 times 10, we should get 17,576,000, okay? So how does this change for the second one? It's similar, but it's no repetition, okay? So we still want 3 letters, and then we still want 3 digits, but we can't repeat. So if we pick our first letter, we have 26 letters of the alphabet. We have 26 choices for that first letter. But if I don't want to repeat the letter, so let's say I pick a letter, the letter A, I can't use that letter anymore for my second choice. So now I only have 25 letters to choose from. Okay, so if my first letter is A, my first letter is B, now the next letter can be any of the remaining letters, just not the A or B. So 26 now minus 2 is 24. I have one less option, okay? And the same for the digits. I had all 10 to choose from, but then when I pick one, I can't use it again, so now I have 9. And now I've picked those two and I can't use those, so now I have one less, which is 8. So the idea is the same. We're multiplying by how many choices we have each time. And so here, these are the way we get those choices. You multiply all of these numbers, and we should get 11,232,000 for this one. Okay, so let's do another one. So we're going to find the number of 6-member committees that can be formed from a group of people consisting of 7 women and 8 men if the committee must have 4 women and 2 men. Okay, so how do we start working on this one? Solution. Well, let's look at it. We want 7 women. Oh, no, from 7 women. I'm sorry. We have 7 women and we want 4. Now, if it doesn't talk about order, if you recall, this would be a combination. So combinations and permutations, we're picking from the same group. We have so many in the group and we're picking from that, right? So I'm here picking from 7 women that I have. I want 4. So it's from 7, we're going to choose 4. Now, it would be a permutation if they mentioned something about the order or putting them in a certain arrangement, but it doesn't. So to find this one, it's going to be a combination, 7, choose 4 for the women, okay? There's 8 men and we need 2. So again, it's not telling us anything about the order of the men or certain positions. So this is also a combination of 8. We're going to choose 2 because again, they're from that same group. Of the 8 men, we're picking 2 from there. So recall the formula we have for the combination. NCR, we have n factorial over n minus r factorial times r factorial. So I can plug these values into that equation. So for 7, choose 4, it's 7 factorial over 7 minus 4 factorial times 4 factorial. If we simplify all that, we get 35. So 35 is the number of ways there are of picking the women. From the 7, how many ways can I pick? 4, 35. Okay. For picking the men, I want 8. From 8, I want to choose 2. So I plug the values into the formula appropriately. Simplifying that, I get 28. But now I need to multiply these. These are just the ways of picking the women. These are the ways to pick the men. So how many ways can you pick the 6 members, right? Well, now you multiply. 35 times 28. So it's the counting principle within the counting principle, right? The counting principle is you multiply all the possibilities. So this is the way to pick the women. This is the number of ways to pick the men. And we multiply to get the value at the end, the 980. Okay, so we're finishing up with a probability. We're going to look at the probability for a pair of dice rolled, where A, you roll a sum larger than 4, and then B, you roll a sum larger than 12. Well, if you recall previously, I had another table like this where you look at the combinations of die, right? So you have, this would be the face of one die, 1 through 6. Here's the other die. And they write them here as an ordered pair. So if you roll a 1 and a 1, you write 1, 1. You roll a 2 and a 1, you write 2, 1, and so on and so forth. So these are all our possibilities, our sample space. These are all our possibilities for the die, right? We're going to look at A, probability of rolling a sum larger than 4. Okay, the sample space here includes 36 options. There's 36 possibilities for rolling the 2 die. Okay, remember that probability of an event is the number in that event that we're talking about divided by the number in the sample space or all the possibilities, right? So for this one, I want a probability of a sum larger than 4, okay? Sums larger than 4 are going to be 5 and on. The biggest one comes from 6 and 6, which is 12. So I want a sum that's larger than 4. So again, I want a sum that's 5, 6, and so on up to 12. So let's see how many we have. Okay, all of these in the diagonal, and it works out nicely when we write it like this. All of the values in the diagonal have the same sum. So all of these outputs right here have a sum of 5. 4 and 1, 2, 3, 3, 2. So that's 1, 2. That's 4 possibilities with a sum of 5. All of these in this diagonal have a sum of 6. That's 1, 2, 3, 4. That's 5 of them. For a sum of 7, it's all of these in this diagonal. There's 6 of those. All of these in this diagonal have a sum of 8. There's 5 of those. All of these in this diagonal have a sum of 9. There's 4. There's 3 with a sum of 10. These two have a sum of 11. And then this last one has a sum of 12. So I basically just counted and added up how many of all of these sums, how many are larger than 4, added them all up, and I have 30. So out of all of these 36 possibilities, 30 of them meet this criteria that their sum is larger than 4. So again, the number in our event is 30. Out of all possibilities is 36. That's our probability, but you always round. So if we divide here reduce, you always reduce. So 30 over 36 reduces to 5 over 6, dividing both by 6. Okay. The second one, part B, what's the probability of rolling a sum larger than 12? Well, we look at all our possible outcomes and we see how many meet the criteria. How many of them gives us a sum larger than 12, okay? So same thing, sample space is 36. It's the favorable outcomes over sample space over total possibilities. Now, if you notice though, none of these is larger than 12. We start here with a sum of 2, a sum of 3, so on and so forth, sum of 11, sum of 12. We do not go larger than 12. So none of these outcomes meets that criteria that the sum is larger than 12. So it's actually 0 out of 36, which reduces to 0. So the probability of that happening is 0. There's no way it's going to happen. That's not possible. Okay. Okay, one more example. Assume that the probability of a couple having a baby boy is the same probability of the couple having a baby girl. If the couple has 3 children, we're going to find the probability that at least 2 of them are girls. So we have options here. To find the sample space, we can also draw a tree diagram. So let's look at that. We did not go over that in the last video, so it's good to review that. So if you're going to have 3 children, how do we draw a tree diagram? Well, we write out the possibilities of the first one, right? So the first branch is the first child, right? That first option. So what are our options here for your first child? You could have either a boy or a girl. Okay. And then we're going to branch out again to show the second options, right? So let's say I have a boy, that's the first child. Then what are my options for the second child? What are the possibilities for the second child? Well, it could be a boy or a girl again. So following along, this is the first, let's say the first was a boy. Following this branch, then I have a boy the second time. But then I'm going to branch out to show my possibilities the third time. And, well, I guess I went over here next, but we're going to branch out over here and show that from here, the possibilities are boy or girl as well, okay? But from every one, from every possibility, we branch out again to show the possibilities for the next one. So here, let's say I had a girl. After having the girl, what are the next options for the second one? Also a boy and a girl, okay? And then again, if we follow any of these, we have this represents our first option. These represent our second possibility. And now for the third one, if we branch out, right? What is the possibilities for the next ones? A boy or a girl as well. So the same from here, it branches out. You can have a boy or a girl. So again, we follow the line. If we had a girl first and a boy second, what are the possibilities for the next one? Same, boy, girl. And if I had a girl first, a girl second, branch out for the third option, still boy or girl. So this is another way to show all the possibilities, and following each of the branches shows all of your options. So if I start with my having a boy, then I have another boy, then my third option is also I have a boy, then I had a boy, a boy, a boy. I had 3 boys. If we follow this again, you had a boy first, a boy second, and then a girl, BBG. Following this branch here, it would be a boy first, then a girl, and then a boy. Following this branch down here, it's going to be boy, girl, girl. And we can continue on following along, girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl for the last one. So this is showing you all your possibilities. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. So again, you start with your option for the first one. We had boy, girl. Then you branch out from each of those. What are your options for the second one? Boy, girl. Then you branch out from each of those and write your options. And then you're going to follow along all of your branches and write down all the possibilities. Okay. So again, as I mentioned, there's 8 possibilities here. Okay. It's asking for the probability that at least 2 are girls. So I go through and look how many of these have 2 G's for girls. Okay, so right here I have a B, G, G for boy, girl, girl, 2 girls. Right here I have a girl, boy, girl, I have 2 girls. Here I have 2 girls. Here I have 3 girls, so at least 2 of them, so I have at least 2, right? So how many of those are favorable outcomes? That's 4. 4 favorable out of our total, which is 8, always reduce. So our probability was, again, the number of favorable events, favorable outcomes, which is the 4, which is the ones with the 2 girls, out of the total possible outcomes, which is 8, reduces to 1/2. So here's using probability, but with a tree diagram to help us get the probability. Okay. So that was it. That covers a bit of a review for the last few sections. Good luck to those of you taking an exam. And as always, you can come visit any of the tutoring centers as well as your instructor if you have any other questions.
Thank you, Ms. Camarillo. Thank you, everyone, for coming in today. Let me go ahead and share next week's sessions. So the 1 o'clock session today, we had canceled. However, we will be back next week on April 24th for Happy Math Hour, as well as the 1 p.m. session with the United Way. Thank you all for coming in today, and I hope you have a lovely weekend.
Thank you. Have a good weekend.